We shall now consider mechanical energies by looking at the work-energy theorem. When we refer to mechanical energies, that doesn't necessarily have to involve machines. In fact, energies that we already know, such as gravitational potential energy, elastic potential energy, which are both types of potential energy, and kinetic energy, are types of mechanical energy. We will now consider the work-energy theorem as it applies to gravitational potential energy. Consider a mass m resting on the ground. In order to lift that mass, we require a force that is at least equal to the weight, so therefore a force equal to mg. And if that force causes the object to move through a distance h, then an amount of work will be done. According to the work-energy theorem, the amount of work done is equal to the energy transferred. So the amount of work done is equal to the force applied, which is equal to mg, times the distance moved in the direction of the force, which is h. Note that the direction of the displacement and the direction of the force is the same. Therefore, cos theta will be the cos of 0, which is 1. We call the energy transferred to the body gravitational potential energy, and we find it using the equation mg times the change in height. We shall now consider kinetic energy. If we act a force F on a frictionless surface on a body, the body will then accelerate. If that force causes a displacement of the body distance d, then it does an amount of work, and therefore energy transferred. As the body is moving, it has energy of motion. We call this energy kinetic energy. It can easily be shown that the work done on the body, which is equal to the amount of energy transferred to it, is given by 1/2 times the mass times the velocity squared. Using the kinetic energy equation to guide your thinking, you can easily see that if the velocity of the object is doubled, then the velocity squared becomes 2v all squared. So the kinetic energy increases 4 times. Similarly, if the velocity is made 3 times as big, the kinetic energy increases by 3 squared, which is 9 times. Or if the kinetic energy becomes 16 times bigger, it is the result of the velocity becoming 4 times larger. We shall now look at another type of potential energy called elastic potential energy. This is energy stored in stretched springs or compressed springs, rubber bands, or anything else that shows flexibility. We can see that when a force is applied, it causes a displacement to either compress the spring in the direction of the force or extend the spring in the direction of the force again. So the work done, which is equal to the energy that is transferred to the body, is found by the force times the distance being x, and the force applied, because it will vary with increasing compression, the average force will be 1/2 times F times x. We can measure the energy by using the equation work done equals 1/2 Fx, and therefore the energy stored in the spring is also 1/2 F times the compression distance, x, or 1/2 kx squared, where k is the spring constant. We shall be looking at elastic potential energy in more detail in a later video. We have now looked at the 3 types of mechanical energies that we shall be considering. That is, 2 types of potential energy, gravitational potential energy and elastic potential energy, and also kinetic energy. So the total mechanical energy of the body is the sum of all these 3 energies. It may have gravitational energy, it may have kinetic energy, it may have elastic potential energy. it may have only one or two of these. So the total mechanical energy of a body is the sum of its kinetic and potential energies. That means that we can say that total mechanical energy equals kinetic energy plus gravitational potential plus elastic potential. Now, a body may have all three of these, or it may have just one or two of them. We can therefore put the equation forms for kinetic energy, gravitational potential energy, and elastic potential energy, which can also take the form of a half Fx. Now, the important thing about mechanical energy is the fact that the total mechanical energy of a body is conserved. Conserved means that it is neither lost nor created, but remains the same. In the case that no work is done, so that energy is added or removed from the system, then the initial mechanical energy, total mechanical energy initial, will be the same as the final mechanical energy, total mechanical energy final. In the case, however, work is done on the body, then to the total initial mechanical energy, if work is done, this will add to the energy to the body if the work done is positive, or subtract from the energy of the body if the work done is negative. Therefore, the final total mechanical energy of the body will either be more or less. In summary, we can say that it's always applicable that the total mechanical energy initially plus any work done on the body will equal to the final mechanical energy of the body. Now remember, the body may have in its total mechanical energy all three of kinetic, potential, and elastic potential, or it may just have one of these. We now need to look at the application of this work energy theorem.